the multiple choice is like 60 points. So is that?
This is out of 100%,
Oh, okay.
just to give a better scale. Yeah. All right, cool. So, welcome, y'all. Most of us remembered that today still has school. My high school didn't, so I am refreshed. This is the most refreshed you'll ever see me. If you may have noticed, as the week goes on, I get more and more tired. But I'm vibrant today. So, this is our distribution for the multiple choice portion. A reminder that the free response is going to take, hopefully, maximum 2 weeks to grade, and then we'll have that. I'm really happy, honestly, with this. Like, as weird as that's at 68, ideally, in my mind, well, I don't know what the ideal average is. I guess my ideal average is everyone gets 100. Like, that's the ideal. The reality is there's always going to be a variation. And I suppose, in that case, the ideal variation would be an average of 75 or so. But if it was above that, I wouldn't lower it. So, you may look at that and say, oh, that's why you curved at 6 points. But that is not true. That is not actually why the 6-point curve is there. So this is out of 100%, just to give us a sense of, how many you got right, as opposed to making it out of 60. The multiple choice is only worth 60% of the thing, whatever. 100%. 100% means all of them correct. 0% means none of them correct. Honestly, very challenging to get none of them correct. Like, that would actually be impressive. You would kind of have to almost do it purposely, because it is a 1 in 4 chance on average. So, how do you interpret this? How do you make sense of your grade? Like, why did I put this up here? Why did I put up this here without the curve? Because what you should kind of take away from this, if you have above a 60% on this multiple choice, that means you have somewhat of an understanding on it. Above a 60%, so 60% is not my threshold, where if you're below that, there is a concern. If you're below a 60%, there is a concern. You can actually still pass my class potentially, with some of the extra credit stuff, potentially with a B, if you're below 60% averages on tests. But if you do the math, 50% of the grade of this class is kind of effort. You do the things, you should get those points, the discussions, the clicker questions, all the quizzes, all that jazz. If you do the math, if you get all that kind of effort points, if you average a 60 or above on my tests, after the curve and all that kind of stuff, you have a B in the class. That's how it works out, assuming no extra credit or anything like that. If you want an A in the class, the math ends up that you need to average an 80% or above on the tests, assuming, again, no extra credit or anything like that. But on a more kind of holistic scale, the way those points kind of work out as well, that means if you're having below a 60%, and this is all purposefully designed, if you have below a 60%, that's a flag that something is off. Preparation-wise, time-wise, effort-wise, something is off. And that doesn't mean you're a failure. That doesn't mean give up on the class. That's just a flag of something needs to change. Something needs to change in how you prepare. Maybe that's coming to meet during office hours, help room hours. Maybe you didn't do the problem set problems. You need to spend more time on those. It's going to be very person to person. And if you are in that camp and you want to help, you're like, I don't know what to do, come talk to me. I will work with you. There's no shame in that. At the end of the day, all this says is whether you know physics. Physics 1. That's all it says. It has no evaluation on your value as a person. I'm not offended by anyone that scores a low grade. Doesn't bother me one way or the other. So please, if you're in that category, come talk to me. If you're unsure what to do, I want to support you. And then obviously, as you go farther down from 60, again, the more concerning it may be. The flip side, if you're doing above 60, awesome. If you're doing above 80%, so if you scored above an 80% on this, that means you have a solid understanding of the physics I've taught you. So that's a really good sign. That's the flip side of things. If you're above 60, it's decent. Then once you're kind of above 80, that means again, that's why it reflects in the A versus the B. The reason there's a 6-point curve, the reason I chose that, there was 2 questions on the test that less than 50% of people got correct. So, I then deemed that as I did not prepare you well for those questions, therefore I gave you some percentage of those questions. 6 points as opposed to the 10 points. So, the reason for the curve wasn't to get the grade of 75%. It was actually based upon how, as a collective, everyone did across certain questions. And the logic there being, a curve should exist because that means that I have not prepared you in some adequate way. The ideal is that I prepared you great, therefore you all learn great, therefore there's no need for a curve. And so anyway, that's the logic there. I have to wait for the free response. Again, may or may not be. Can't promise any curves on that. That is going to be sent. I'm going to look at the questions, see how people did, evaluate it from there. Okay? So I've asked the grader, and I'm going to actually make them an Excel spreadsheet so that I can see individually how people did, which questions they chose, all that kind of jazz. Another thing to point out, because I want feedback, and the best way to get feedback is to give points for it. I have made a survey for you all from test 1 that is worth 2 bonus points out of 100 points on this test. You don't have to do it. It will not affect your grade negatively in any way. I'll send out an announcement with this. Survey is super easy, super quick. But again, this is for me. The reason I give this survey is just so I can get feedback from you all and have a sense of whether my course design is actually effective or not. So, the first one is how would you rate the difficulty of the test on a scale of 1 to 10. The second one is how much of the problem sets did you solve through. Third one is how prepared did you feel. And the last one, there's a link to a survey that's anonymous that has written out responses. This last part is anonymous. The rest of it I can't really make anonymous. But again, you get the same points. Here, I'll show you. The way I built this is no matter what you answer. Oh, someone already started. Awesome. Every single round of these is worth half a point. You get the points no matter what you answer. I don't care. Again, I'm not offended by how you all feel about this. I'm not going to be looking at individual people. I'm going to look at these responses as a whole. I'm not going to go and hunt through for, how did Joe feel about, no. I'm not worried about that. But this last one is more written out. So I want to give you all a chance to actually, share your honest thoughts in words. You don't have to. If you open that survey, so the way it's going to work is you open the link to that. There's a couple, hey, do you have any thoughts that you want to put in writing? Any extra comments, stuff? If not, write whatever you want. Write we'll make you put something. I don't put a smiley face. I don't care. After you answer that, you can see what code to put on that. It literally will say test 1 at the end, and that's the code you put in. It gives you the code at the end of it, which I kind of showed here. Whatever. Again, I want that feedback from you all. If you have feedback, hopefully you feel inclined to give it. This is for me. And ultimately then benefits you all. All right, do you have any questions about any of this stuff? Yeah.
Are we going to be able to get a spec to see what we did got wrong?
If you come during my office hours, potentially, not this week. So this week I do have people who had excused reasons doing makeups during this time. But next week, for multiple choice, yes, free response, I'm going to have to see. Free response is a little trickier because I have to literally carry around a packet of 200 free responses. I'd be able to show you the grade, but the multiple choice, yeah, I have all those scanned on my phone. It would just take a little bit of hunting, but I could do it. Yeah. Any other questions? Yes.
Do you have the median score?
Do I have the median score? Sure. Let me pull it up my phone. The cool thing with the way I grade this is it gives me all this stuff. The median was a 70. Yeah, median was a 70 before the curve. Standard deviation of 19.3. Let me see that kind of in the spread. Yeah, it's fun. Statistics is fun. I enjoy that kind of stuff, which is why I like it. Anyway, there you go. All right, so today we're going to get into work and kinetic energy. So this week and next week is all about energy. This week and next week is all energy. The week after that, I forget the exact order. I believe it's, I'm going to say it's gravity and, you know what? Why guess on this? Let's just open it real quick. I know exactly what I'm covering. I just forget the exact order. All right, so we are in week 6. Week 8 is, great, momentum. And then the last week will be universal gravity and waves. So this is not test 2. Test 2 is taking place the week you get back from spring break. So have that somewhere in your head. It's on your all syllabus already. The week you get back from spring break. So we have 4 weeks that we're covering stuff. And then we're there, I believe. So, it's going to be great. All right, so what we're talking about with energy, super important concept. Everything in the universe can be explained by energy. Completely made up idea. I mean, a lot of physics it's all made up by humans. It's our way of understanding the world. But energy in particular is a really weird idea where we just like made up this thing and it works. You'll see what I mean as I kind of go through these things. We're going to define what energy is, how it's present, talk about what work is and its relationship to energy, find the energy in a moving object, and then relate work and power together. It's going to be good. All right, so energy. Again, we're going to see a little bit of a circular logic here. So it's something we made up. Takes a bunch of different forms. Can't be created, can't be destroyed. That's a critical concept. That's right up there with mitochondria as the powerhouse of the cell. Is that energy can't be created or destroyed. One of those things that kind of everyone's heard at some point, probably. It is a scalar, which is awesome. That means no vector stuff, y'all. Energy has no direction to it. Energy has no direction to it. When we get to momentum, we're going to have vectors again. But for now, we get to rest in the ease of scalars, don't have to break things into components. And again, it's a weird thing. Energy is a made-up thing. It's something you can kind of so you can feel that something's hot. You can see that something's moving. But all of these energies are calculated from other measurements. As we introduce them, you'll see what I mean. None of these can be necessarily observed. You can't just look at something and say, or if I say something is 300 joules of energy, you look at it and say, yep, I see that. No. Whereas a velocity, I say it's going 10 meters per second. You actually can get a physical sense of what that is. Acceleration, you can kind of see if something's getting faster or slower. Time, you can look at a clock, I guess. Energy is a weird thing where it's all calculated, not necessarily something you can look at and say how much it has. All right? Now, I had to introduce energy because then we're going to get into work, which is based on the definition of energy. They kind of circular logic themselves. Again, it's all kind of made up. Work is the measure of energy transferred. So it's how much energy is transferred to something. That's kind of the major piece here. How much energy is transferred to something? How? By applying force over some distance. Work is the energy transferred to something by applying some force over a distance. The symbol for work, very nice, is W. We are very blessed by that it actually matches. Not all variables do. Work is W, the variable for it. The unit is joules, named after a guy whose last name was Joules. That's how it goes. A lot of physics terms, especially the ones we make up. Remember, forces, kind of a made-up thing by Newton, named after Newton. Joules, made up by a guy whose last name is Joules, gets named after him. The units that are kind of made up get the named after someone. The units that you can kind of, like a meter and stuff like that. Those have been measured for so long because they're so useful. All right, joules is the unit for energy. Thermal energy, measured in joules. Kinetic energy, measured in joules. Potential energy, measured in joules. Potential energy due to a spring, measured in joules. If it's energy, it's joules. And if I'm transferring energy, how much energy am I transferring? Oh, it's joules. So if I'm transferring, it's well, I'm not going to confuse that anymore. Why is work joules? Because it's how much energy is transferred. So it's going to be in the unit of energy. Now, this equation looks all sorts of it's calculus. We love calculus. Woo! You are so blessed that you have calculus in your life. It is the dot product, and that may be something, gosh. Do you all learn dot product when do you learn? Do you learn that in Calc 1? Calc 3? Oh no, alright, that's in the future for y'all. Alright, dot product there's two ways to multiply vectors, so you're going to get a little foreshadowing of Calc 3 things. Dot product is one way to calculate a way of multiplying vectors. Now, I'll show you all, because Dot products always let me go ahead and show you all down here. I kind of have it. If you have any two vectors, A dot B, so there's two ways to multiply vectors. There's dot products and there's cross products. We'll worry about cross products when we get to it. This X is not strictly multiplication. It's called a cross product between vectors, whatever. For now, let's just worry about the dot product. The dot product between two vectors equals the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. So if I have two vectors and I want to get this is one way of multiplying it. There's two ways. This is one way. Now there's a cross product. That's future. Magnitude of A, meaning square root of x squared plus y squared plus z squared. You got to get its magnitude. How big is that arrow? Times the magnitude of the other one times cosine theta. Okay. For some reason, it took me a long time to get this realization. But let me show you all what's happening in a dot product. Because this is just math right now. It doesn't really have much meaning. Maybe hard to understand the meaning here. Let's just draw these vectors. So here's vector A. And here's vector B. What is happening when you're doing a dot product? Let's just rearrange this a little bit. I'm going to rearrange this. It's multiplication. I'm allowed. B times A cosine theta. If I multiply A times cosine of theta, here's what happens. If I multiply A times cosine of theta, I get the adjacent side of the triangle. This is A times cosine of theta. It's the x component, you could think about it. So when you are doing a dot product, all you're doing is you're finding the component of the vectors that line up with each other. How much do the vectors line up with each other? And then you multiply them together. So we take the part of A that is parallel to B, we take the component of A that's parallel to B, and we just multiply those two numbers together. The dot product is A cosine theta times B. So that's what's happening here. You can kind of see the extreme case. If A and B were parallel, the angle is 0, cosine of 0 is 1. It's just A times B. If A and B are perpendicular, cosine of 90 is 0. There is no component of A that lines up with B. So this is just like a visual way. What is a dot product? It's finding the parts of the vectors that are parallel to each other and multiplying them. That's it. If that didn't make any sense to you, you don't need to understand that, but I hope for some of you that'll make dot products a little bit more understandable, because this is something that took me a long time to kind of I don't know, no one ever told me this. I kind of had to stumble my way into it. Yeah?
How do you find theta? If A and B are both, would you just add the direction of A and B to get theta?
So A and B, it'll be given generally. It'll say the angle between these is 30 degrees. Yeah, so the angle will generally be given. Yep, that's a great question. So, okay, that's a little bit of math. Dot products. Yeah.
What if one of them isn't on an axis?
Sure. What's really cool here, if I take this picture and I rotate it, oh, it doesn't let me rotate it. That's so sad. All right, if I just draw the same picture but rotate it, let's say we have A up here and B, this way. It's the exact same thing. I conveniently drew them. Actually, I did figure out a way to do this. So if I took this and I made it a picture and I rotated it, the same relationship holds. How do I check this? Down here. So it doesn't matter which way they're pointed, because when you do this cosine of this, you get the part of it that lines up with B. Either way. Yeah, that's a great question. So it doesn't matter which way they're pointed. By doing that cosine of it, you're finding the part of one that's parallel to the other. All right, so physics, great. That's math lesson for you all. You'll see it again in Calc 3 at some point. What does this have to do with physics? Okay, work is defined as the integral of the force dot dr. It's a force over a distance. Why do we have to do an integral? Because what if my distance, what if my direction changes? What if my force changes? An integral is a fancy way of summing up things. An integral is just a very fancy way of adding up things. So, by doing an integral, what we can do is we can account for all the craziness that might happen. What if my force is changing over the distance? As it travels, the force is increasing. That can happen. What if my direction is changing? This dot product accounts for that changing direction. So anyhow, we got to do this integral. The simplest case, if the force is constant and the direction it's going is constant, the integral just becomes, if the force is constant, let's just kind of pull this out. F is constant. The angle is constant. That gets pulled out. The integral of dr just ends up being whatever distance you go. We'll call it d for distance. Okay? So if it's a constant, you just get fd cosine theta. That's down here. What matters here? What matters here? All this dot product stuff, why do we have to do the dot product? The force needs to be contributing to this thing moving. This force needs to be, remember I told you also the part that's parallel to it? So this whole dot product is saying what part of the force is in the direction of motion? What part of the force is in the direction of motion? That's how I get the work done to it. That's how I get how much it's contributing to it. If my force is directly upwards, it is not contributing to this thing moving to the right. And if my object doesn't move up or down, the force is not adding or taking away any energy. If I push this cart across the room, and I'm lifting it right now, you can't tell, it's not very obvious, but I'm slightly lifting this thing is not lifting in the air. Therefore, the amount that I'm pushing up is doing nothing energy-wise. It is not adding any energy to the system. We're going to learn that the ways you add in, there's a few ways to add energy to a system. One of them is lifting something. So if I lift something higher, I'm applying a force upwards and it's moving upwards. The force in the direction it's going line up. I'm adding energy. The other way, one other thing we can get energy from is making something go faster. If I push it in the direction it's moving, it will get faster. That's another way. I'm adding energy. Work is all about transferring energy, increasing energy, decreasing energy. If the direction you're pushing, it's not moving that way, you're not doing anything to it. Yeah.
Is there a reason why one of the reasons why it's easier to push something this way than something this stationary?
That one gets into static and kinetic friction, and that's just more of the bumpiness of a surface. But I like that. Yeah, I like the thought there, though. Yeah, that one gets more into friction, though. But good question, though. Okay, so work. Just spent a lot of time on this definition. We're going to do some math practice with it. All this talk I do is to help you all have a conceptual understanding of it, and that takes time. Some of you it's going to click. Some of you it's going to take longer. Some of you it may not click. The reality is when it comes to physics, at first, if you can just do the math, that's great. But the more conceptual the more you understand why you're doing it, the easier it is. And as time goes on in your engineering / whatever your major is, you're going to find that out. At first, sometimes you just say, okay, this is what it is. It's this math. I don't know why, but whatever. I do the math. And then as time goes on, as you use it more and more, you start to understand the why more. And again, that clicks at different points. What causes it to click is different for every single person. All right, so I hold a 10 kilogram weight above my head for 5 minutes. How much work did I do? Model this for you all. This thing is not 10 kilograms. I hold this chair above my head. That's also not 10 kilograms. Reminder for you all, a kilogram is about 2.2 pounds, even though kilograms isn't mass, whatever, on Earth, that's how it works out. So I hold an object. I'm totally not going to hold this thing for 5 minutes, because that's awful. But this is the idea. I hold it here for whatever time I said, 5 minutes? 5 minutes. How much work did I do? That's what this question is asking. How much work did I do while I held it above my head? Is it 50 joules, 3,000 joules, 0 joules, or 2 joules? That's a classic question. All right, we'll go to 120 on this. All right. And 5, 4, 3, 2, 1. All right, for us to calculate this, shocking, you know what's our givens? We got mass. We've got time. Technically, we'd need to convert that, but you know what? I'm going to spoiler alert. We don't need to convert it. Work equals the integral of force dot dr. All right, I'm holding something above my head. I am supplying a force. What is that force? M times G. The force that gravity is pushing down on the chair is the same force I'm pushing up with it. Dot. This mg is going to be downwards. It's in the y-hat direction. Dot dr. But here's something interesting. I need boundaries for my integral. Where does my thing start? You know, let's make up a number. Let's say it starts 2 meters above my head. Oh, where is it later? Oh, it's still 2 meters above my head. Again, I'm kind of writing this out just to get us used to the integral. So we have the integral of dr, which we just said is going to be mg times the distance. It didn't move. Zero joules. Yes, my arms were getting tired holding up that thing above my head. That is a thing. Work here, and that gets really complicated. Inside my body, there is work happening. Like there's molecules and the muscles are doing things, and that's really complex. But on a whole, my whole body, what's going on here? It's not moving. Even though I'm applying a force, it is not moving anywhere. I am not causing this chair to gain or lose any energy when it's above my head. That's what work is. Work is all about, am I causing something to gain or lose energy? No. I am not applying a force. I am applying a force. I'm not applying a force to cause it to move any distance. It is not moving at all. That's the key here. And that throws a lot of people for a loop because we think work and we think work is tiring, and therefore we think lifting something above your head is tiring, and all of that is true. But this is where the science definitions, you have to be, the wording here is precise. Work isn't about whether it makes you tired. Work is about whether or not you're adding or taking away energy from the system, whether you're applying a force over a distance. Okay. Funky idea. And the math matches that. All right, so what's doing the work? If there's a force and an object is moving, then work is, if there's a force in the direction an object is moving, let's even be more specific, with a component that is in the direction, it doesn't have to be pointed exactly the same way. As long as a piece of it, I could have a force that's like pointed almost vertically. Key phrase there is almost. If my thing is moving to the right, there is work being done there because there is a component of the force that lines up with it. As long as a piece of it is in that direction, whatever is causing the force is doing the work. So, if I am pushing something, I am doing the work. If friction is opposing me, friction is also doing work. If gravity is pulling it down, that's doing the work. Work does not have to be done by a living organism. Again, science definitions. Work is any force, and gravity is a force. When gravity causes something to fall, this marker falling, it is doing work. It is transferring the energy from one type to another. We'll learn about that. And yeah, we may have to draw a free body diagram to determine the forces. If we want net work, we need net force. Classic. See, it's all connecting together. If you want to figure out the net work done, is this thing gaining or losing energy? You need all the forces. If the net force is 0, your object is not gaining energy. Individual pieces of it, so like a car going 60 miles per hour at a constant speed. The applied force from the engine is doing work, positive work, because it's pushing the car in the direction the car is moving. Whereas friction is doing negative work. So this is a good kind of example to draw out. I got a car. The car is getting pushed forward by, the engine. It's getting slowed down by friction. The car is moving to the right. So your distance is to the right. Friction here is doing a negative work. Why? The angle between the distance and FF is 180. Cosine of 180 is negative. So, let's just calculate both those. I say calculate. So work equals FA times D times cosine of theta. Cosine of theta is going to be 0. So great, I get FAD. If I do the work due to friction, I have FF times D times cosine of theta. That's 180 degrees. That ends up being a negative work. So this is something you have to be able to do. Is the work positive or negative? It's really simple. Is the force in the direction it's moving, or is the force in the opposite direction it's moving? Why does that matter? Because the angle matters. Cosine of theta is in there. Cosine of 180 is negative 1. Cosine of 0 is positive 1. Okay, so it comes out from the math. But again, are you kind of increasing its energy or decreasing its energy? That also plays into things here. All right, so we're spending a lot of time on the concepts here because honestly, the math isn't too bad on these. Like this. You'll see the section, it's not too bad, but the concepts are the hard part. Yeah.
Why don't you break an R?
I could put R instead of D. We just tend to think of D as distance instead of R as distance. Yeah, I could put this as an R if I had wanted to instead. Yeah, the funky thing with measuring distance, we have so many variables for it now. X, Y, D, R. You just kind of pick one at some point. Yeah.
So it's only scalar at this point?
After you do the dot product, it becomes a scalar. So the way I wrote these, and that's a really good point actually. After you do a dot product, it turns into a scalar. So force is a vector, dr is a vector. After you do the dot product, it turns into a scalar. That's a great point that I actually forgot to mention. Yeah. Yeah.
So dr is the d in the integral is derivative. Dr is
So that's a good question. Dr is an infinitesimally small distance. And then if I summed up all those small distances, I get the total distance, which I just call d. So dr is an infinitesimally small movement. Yeah. Displacement, basically. Yeah, an infinitesimally small displacement. All right, let's do one or two more. Oh, it did the thing. We love it when it does the thing. All right, let me save all my hard work. And then close and reopen this. So the next question, again, you can see the ghosts. An object is falling through the air. What is doing work on the object? So I'll give you all a couple seconds to think about that while I reopen this. An object is falling through the air. What is doing work on it? You know what's exciting? This is our exact halfway week as far as content is concerned. It's fun. After this week, we're over the halfway point as far as what I need to teach you in the class.
After this week, halfway?
Yeah, I guess technically this Wednesday is like dead halfway. Yeah, I have 11 weeks of stuff teaching you all, so... Oh, wait. No, we're running out there. No, we're going to get to 5.5. Yeah, halfway through this week. Yeah. I've covered half the content in the class. Kind of, sort of. Yeah, no. Is it actually half? All right. We'll wait 5 more seconds, or we'll go to 45. I'll wait 2 more seconds. And 5, 4, 3, 2, 1. This is a little bit of a trick question. Everyone seemed to pick mainly one of them. So, something's going through the air. Boom, there it is. It's going downwards. So, again, we can do like dr is downwards or d is down, whatever. The forces are constant. Let's just say, can't really draw a vector for dr because it's infinitesimally small, so that gets kind of funky. So we'll just do d for it's moving downwards. Let's draw a free body diagram. Forces, gravity, yep. Air resistance, we'll just call that friction. Air resistance is a form of it. So which one's doing work? Both of them. They are both doing work. One, gravity is doing positive work. Why is it positive? Because it's in the direction it's going. Friction is doing negative work because it's opposite the direction it's going. What does that mean? Gravity is kind of transferring some energy to some way, and this friction is kind of opposing that. That's what negative work tends to kind of give you a sense of. Well, and we're going to have a better sense of what it is when I give you all the theorem for this. It's called the work energy theorem. All right, so calculate the work done on a 1,500 kilogram elevator by its cables to lift it 40 meters at a constant speed, assuming friction averages 100 newtons. What is the work done on the elevator car by the gravitational? What is the work done total? All right. First step, draw a free body diagram. So we got our elevator. We have some force that's pulling it upwards. We have gravity pulling it downwards. And it says it is getting lifted. So I'm going to give you all 10 seconds. Which way is friction pointed? Think about it for a few seconds. Which way is friction pointed? It doesn't tell you in the problems. You have to be able to think through it. If it's getting lifted, friction is always opposite the direction of motion. Always. Force of friction is downwards because it's going upwards. All right, so we got that. What's our givens? We have the mass is 1,500 kilograms. We have G is 9.8. Now, when we do forces, this is the part where we're just going to put G as a positive 9.8. Remember, and you may have encountered that when you were doing the forces stuff, we're just going to put G as positive 9.8 because we're going to define gravity as downwards, and that's already accounted for. If you double count it, you run into problems. Okay? When it comes to kinematics, you should put it as negative. Basically, in everything else, put it as positive, define direction separately. All right, we have our distance is 40 meters. We know our acceleration is 0. It is moving at a constant speed. That was a little subtle, but it's there. The force due to friction is actually given 100 newtons. And that seems to be all the numbers. If we need more, we'll come back and add them. First step, find the work done by its cable. So we want the work done by the cable. Equals question mark. Step 3, our equation for work is the integral of F dot dr. Now, if you know that it's constant, if you know the force is constant, meaning I didn't give you an equation for the force, if you know that the distance is in the same direction, this simplifies to F d cosine theta, so constant F, whatever. If things are constant, you'll know when they're not constant, because I'll straight up give you an equation that says, here's the equation for force, and it'll have x's in it, thereby showing you it's not constant. Okay. Now, if I jump to step 4, I can say work equals, and I immediately run into a problem. I don't know the force it's pulling up with yet. So we look at this and say, I want to start plugging in numbers. I don't have the applied force pulling it upwards. Oh, okay, guess I got to find that. How do we find that? Oh, so good. The sum of the forces equals mass times acceleration. Good review. We love this, right? It's good to keep this in your mind. This does not go away. This whole sum of forces equals m times a is a very, very important thing for everyone in this room. If you're in any engineering whatsoever, you're gonna use this a bunch. If you're not, well, you need it in this class at least. All right, so if we write this out, we have the applied force is upwards minus the force of friction minus the force of gravity equals 0. The acceleration is 0. It is moving at a constant speed. Again, that's that. Keep velocity and acceleration, keep them separated in your brain. Oil and water, not the same thing. All right, so then we're going to use this to find FA. So FA minus 100 minus 1500 times G. Again, this is where if we put that negative for 9.8, you're double dipping. Don't double dip. And we'll get FA equals a number. Yeah, and there's no way I'm going to try to do 1500. No, let's say that. Thank goodness I've got a backpack full of extra calculators. My calculator batteries died. I have extra batteries in my backpack. I'll add them later. Pro tip, y'all, always check your battery calculators. Or calculator batteries, whatever, words. All right, 1480. 14,800. Yeah, actually, I say I owe too early. We'll get to it. All right, great. That seems reasonable. It's a big elevator. Makes sense that I got to put a lot of force into it. All right, now we get to use that. Work equals 14,800. The absolute value of that is what it is, times the distance it travels. These are in the same direction. And that's the last thing. Oh, what's my angle? Well, my thing is going upwards. So you all spend 10 seconds. What is the angle between FA and the direction it's going? It's 0. They're parallel. That is something that isn't given in the problem, but that's where we realize, they're parallel. Cosine of 0 is just 1, but you can just plug this whole thing in your calculator. If you're like, man, I don't remember what cosine of 0 is, just plug it in. We get 592,000 joules. Again, energy is a weird thing. Like how much energy? Is that a lot of energy? Is that a little energy? Here's to give you all a sense of energy. If we just do a quick calculation, say I want to figure out how much energy, let's just say this water bottle is 1 kilogram. To lift 1 kilogram, if we just use the equation F equal, the energy gained is F times D times cosine theta. The energy to lift 1 kilogram object 1 meter is 9.8 joules. So to lift a 2-pound object 1 meter, it gains 2 joules. So that's a nice reference, or not 9.8 joules. So 10 joules to lift a 1 kilogram object 1 meter. It gives you a frame of reference. Always useful. So that way when you hear joules, you have a sense of whether it's a lot or a little or stuff like that. And you can always do stuff like this. Anytime you'll ever have a calculation with the new unit, just make up numbers. Make up an example. To get a frame of reference for it, make up, like I just did, a 1 kilogram object. So that's mass times gravity times 1 meter height. Whatever. I'm going to erase that so people aren't super confused later on. 9.8 joules though. There you go. All right. Let us look at... there's more here. What is the work done by the gravitational force? You just do mg times the distance, but it'll be negative because fg is downwards, distance is upwards. What is the work done total? Super easy. What's my net force? My net force was 0. Who cares? Like, so what's my work done? Net work, 0. So, the net work done on the elevator car is 0. Wild. Alright. That's because gravity is pulling it down, friction is pulling it down, applied force is upwards. Okay, here we go. Told y'all. How do you know when the force is not constant? When you have an equation for it. An object is pushed with a force of 6x squared over a distance of x. What is the work done? You have to do some calculus. I'll write the equation on the board for y'all. You're finding work. Work equals the integral of f dot dr. We will assume that these are in the same direction. We'll assume these are in the same direction. So therefore, it gets rid of our dot product for us. It gets rid of the cosine theta for us. We will assume the angle between these is 0. So it simplifies it for us. Theta is 0. Doesn't say that in the problem. You have to... So that's what I told y'all. But I love these kind of problems because you get to do calculus and physics, but neither is necessarily that complicated. You all will get to a point where the calculus involved gets, you know, like the problems get more advanced, the calculus gets more advanced. Yeah.
I don't know what I'm doing, but isn't supposed to be 2x?
Oh man, I checked this too. Man, I sure want, let's just change a bunch of things. Let's just change a bunch of things, so then you can't tell what the answer should be. Yeah, that's, oh man, I looked over this turn, I was like, oh yeah, no, I did good. No, I didn't. That's why, yeah, even when you double check your work, sometimes it happens. That is also why it is super impressive if you ever get a perfect score on anything in life. Because it's so, oh gosh, it's so easy to make mistakes. I checked your all's test 4 or 5 times for typos, and there were still 2 tiny typos on it. Thankfully, they didn't affect much. But it happens. All right, we'll go to 240. People online, you know, hopefully they had time to see the corrected. 5, 4, 3, 2, 1. All right, so the key to this is doing calculus. Nothing more to say here. Work equals the integral of my f, which is 6x squared. And this is where I told you all, there is so many variables for distance. dr is dx. They are the same thing. dr is just an infinitesimally small distance. In this problem, I'm only moving in the x, so dr becomes dx. R technically is like includes all the dimensions, x, y, z, but we're only moving in the x, so it simplifies. If you wanted to get real awful, so this is just, well, let me solve this one and then I'll show you what gets real awful. So it's going over distance x, so my boundaries are 0 to x. So I get an integral, you integrate this, you get 2x cubed from 0 to x, which ends up being 2x cubed. We'll plug those on in. So, bam, one dimensional. I am not going to go crazy. You all are very fortunate that we haven't, Calc 2 is not a requirement yet, so double integrals has not come into play. I think that's actually Calc 3. Yeah, so a more extreme version of this, I'm not going to do this to you all. But say I gave you a force that was x, y, z squared. Who cares? All the dimensions. And you wanted to do this integral. It would be a triple integral. Because dr is technically, you know, whatever dimensions, whatever. And that looks, that integral is actually very easy to solve. But you haven't learned about triple integrals. Fun fact, it's just doing an integral 3 times. Ooh. Calc 3 is so much better than Calc 2. All right. Anywho, there you go, y'all. We talked about work. We talked about energy. We'll talk about kinetic energy and then connect them. And yeah, hopefully energy is feeling like an okay thing with y'all. We'll see, or at least work is. Have a great rest of your day, y'all. See you Wednesday. I will not be as energetic.
So I'm thinking about taking Calc 3 and statics over the